All right, we are continuing talking about linear systems of equations. In the last video, you looked at how to solve them through the graphical method. Today, we're going to look at the substitution method. Or not today, in this video we will. Now, there are 3 steps you need to follow. First, we're going to solve one equation for one of the variables. And it doesn't matter which one. In your note packet it says solve either equation. You just need to solve one of them for one variable. The second thing you're going to do is you're going to substitute this expression from step 1 into the other equation. So the equation is in terms of just one variable. And then you're going to solve for that variable. And the last thing you're going to do is use substitution to solve for the other variable. So whatever you got from step 2, you plug into one of your original equations, and you can find the second variable. So let's actually jump right into our first example. In our note packet, it's example 5. We're going to have the system x minus 5y equals 13, and the equation negative 7x plus 8y equals negative 10. Now, my hint when doing this is if you have any variable anywhere in one of the equations where the coefficient is 1, so there's no number visually shown in front of it, solve for that one in that equation. So in this case, I'm going to solve for x in my first equation. So I'm going to add 5y to both sides of that equation. We're going to get x is equal to 5y plus 13. Now we're going to take that 5y plus 13 and put it into for x in the other equation. So we're going to have negative 7 times 5y plus 13 plus 8y equals negative 10. We can distribute the negative 7 and get a negative 35y plus 7 times 13. That gives us negative 91. So we're not going to have plus, we're going to have minus 91 plus 8y equals negative 10. Then we can combine like terms. Negative 35y plus 8y, that combines to make negative 27y minus 91 equals negative 10. We can add 91. We'll have negative 27y equals 81. And if we divide by negative 27, we're going to get y is equal to negative 3. Now to figure out x, we're going to take negative 3 and put it into one of the original equations. I'm even going to take a little shortcut and I'm going to put it into the blue equation we wrote. So x is going to equal 5 times negative 3 plus 13, which means that's negative 15 plus 13, which means it's negative 2. So our ordered pair, since that's what x equals, our ordered pair is going to be negative 2, comma negative 3. Let's look at number 6 in our packet. we're going to have 2x minus y equals 16, and 12x plus 5y equals 6, not 5y, just plus 5, equals 6y. Now I notice in the first equation, y, it has a coefficient of -1, but let's solve it for y. So when I solve that equation, I can add y, get 2x equals y plus 16, and then I can subtract 16, get y equals 2x minus 16. So I'm going to plug 2x minus 16 in for y in the other equation. So let's rewrite that equation. We've got 12x plus 5 equals 6 times 2x minus 16. We can distribute this 6. We'll have 12x plus 5 equals 12x minus, so 6 times 16 is 96. So now we solve this for x. We can subtract 12x on both sides. We're going to get 5 equals negative 96. And my question is, can this ever happen? No, 5 can never equal negative 96. If we ever get to a point while we're solving a system of equations like this, where we get one side equal to another and they can't actually equal, this can't happen. We say we have no solution. There is absolutely no number we can plug in for x that would give us a true statement, which means these two lines are parallel. Now let's look at number 7. We've got the system 3x minus 2y equals 30, and 7x plus 5y equals negative 17. Now, in this case, we don't have one of the variables with a coefficient of 1 or even negative 1. So we need to solve for one of the variables. I look at this system and I think, if I'm looking at it correctly, if I solve for x in the first equation, it shouldn't be too bad. So we're going to do that. We're going to solve for x, and 3x minus 2y equals 30. So we're going to start by adding 2y to both sides. So we're going to have 3x equals 2y plus 30, and then we can divide by 3, everything by 3. So x is equal to 2/3 y plus 10. We're going to take 2/3 y plus 10 and put it in for x in the other equation. So we're going to have 7 times 2/3 y plus 10 plus 5y equals negative 17. Now we can distribute 7, which is going to give us 7 times 2/3 is 14/3. We just multiply 7 by the numerator. 7 times 10 is 70, plus 5y equals negative 17. Now we could move 70 over right away, and I like that idea. So I'm going to move 70 over by subtracting both sides by 70. So I'm going to have 14/3 y plus 5y equals negative 87. And we're almost there. Now we need to combine those two y terms. Now I'm going to rewrite 5y as 15 over 3y, because our common denominator would be 3. If I multiply the term that has 5y in it by 3 in the numerator and denominator, I get 15y over 3. Now we can combine these. 14 thirds y plus 15 thirds y is equal to 29 thirds y equals negative 87. And we're going to multiply by the reciprocal of 29 over 3. So that means we're going to multiply by 3 over 29. If we do that, the 29s and the 3's on the left side cancel out. And if we just go 87 times 3 and divide that by 29, we're going to get that y is equal to negative 9. Now we're almost done. We just have to solve for x. So I'm going to go and plug it into the first equation. So I'm going to go 3x minus 2 times negative 9, and that has to equal 30. Well, 3x is just going to be 3x. Negative 2 times negative 9 is going to give us a plus 18 equals 30. So if we subtract 18, we're going to get 3x equals 12. Then we can divide both sides by 3 and get x equals 4. So we've now got an x and a y part. Our ordered pair is going to be 4, negative 9. So now let's look at example 8. It's going to be the system negative 4x minus 3y equals negative 21, and 5x plus 9y equals 63. So I'm going to take and solve the first equation for y. You could do whatever you want. I'm just going to solve the first equation for y. So I'm going to go negative 4x minus 3y equals negative 21. So I'm going to add 4x to both sides. I have negative 3y equals 4x minus 21. And I'm going to divide everything by negative 3. So I'm going to have y equals 4 divided by negative 3. We're just going to leave that as negative 4 thirds x. A negative divided by a negative, we've got negative 21 divided by negative 3 is a positive 7. Okay, fractions, they're scary, but we can work with it. So we're going to take this and plug it into the second equation for y. So we're going to have 5x plus 9 times negative 4 over 3 x plus 7 equals 63. We can distribute 9, and if we distribute 9 to 7, that's 63. But if we do 9 with negative 4 thirds, the 3 and the 9 can reduce. So it's going to really just be 3 times negative 4, because 3 goes into 9 3 times. So we're going to have minus 12x. I don't need to put that plus. And then bring our 5x down equals 63. Now if we subtract 63 on both sides, we're going to get 5x minus 12x equals 0. Combine our x terms, we get negative 7x equals 0. Well, the only way for this to happen is if x is 0. So we've got our x value. We're going to plug it into either. It does not matter which of the two original equations. I'm going to go with the second. You can go with the first. So if I go 5 times 0 plus 9y equals 63, we're just trying to figure out y now. 5 times 0 is 0, it's gone. So 9 times y is 63. If we divide by 9, we're going to find that y is equal to 7. So our ordered pair is going to be at the point 0, 7. So we've looked at solving by substitution. If, and there's one case we didn't go over, in fact, I'm going to summarize this substitution method. If we got through this in the first part, x equals a number, that means we're going to have one solution. We can find something. If we get something like 2 equals 3, where that can't happen, we have no solution. And the case we went over both of those. The first case happened in examples 5, 7, and 8. The second one there happened in example 6. This third case, say we get something like 0 equals 0, where it is true, this would be infinite solutions. This was not talked about in any of the examples. We've got one other method of solving a system, and then we're going to look at some word problems on systems. But we'll save that next method for our next video.